When we talk about thermal comfort in buildings, we often focus on air temperature. It's simple, it's familiar, and it's what thermostats display. But here's the thing, air temperature alone doesn't tell us how warm or cold we really feel. You can sit in a room that's 21 degrees and still feel chilly. Or sit in a room that's 28 degrees and feel surprisingly comfortable. The missing piece is something called mean radiant temperature, or MRT, and it's one of the most important and most misunderstood elements of thermal comfort. In this video, we're going to look at what MRT actually is, why it has such a huge influence on how we experience a space, and how architects and engineers estimate it in real buildings. Mean radiant temperature describes the average temperature of all the surfaces around you, weighted by how much heat they radiate toward you. Unlike air temperature, which is all about what you feel through convection, MRT is all about radiation, which is the exchange of infrared heat between your body and the surrounding surfaces. Every surface in a space is constantly radiating heat. Warm windows send heat outwards, cold glass pulls heat from your body, sunlit walls glow with warmth, and shaded corners become cool radiators. Your body absorbs and emits infrared radiation to these surfaces continuously. MRT simply represents the combined net effect of all those interactions. And here's the key, MRT can change dramatically even when the air stays the same. This is why a 21-degree room with cold windows can feel uncomfortable, and why a warm surface hit by the sun can make you feel hot even if the air is cool. Comfort standards like ASHRAE 55 and ISO 7730 treat MRT as equally important as air temperature. That's because the human body loses or gains heat through radiation just as much as through convection. If you've ever stood next to a cold glass facade in winter and felt a chill, even though the thermostat says the room is comfortable, that's MRT at work. Or if you sat near a sunlit wall and felt uncomfortably warm while the air conditioning is blasting, again, that's MRT. In many buildings, the biggest comfort problems aren't caused by the air temperature at all, but by the radiant asymmetry, large temperature differences between surfaces in your field of view. If you open a building physics textbook, you'll see MRT expressed as a formula that combines the temperature of every surface with its view factor, which describes how much radiation from that surface actually reaches you. Mean radiant temperature is calculated using the following formula, where MRT is the mean radiant temperature, Ti is the temperature of each individual surface in the vicinity, and Fi is the view factor of each surface, representing the proportion of its radiation that reaches the person. In theory, you'd account for every surface in the space: walls, ceilings, floors, windows, columns, beams, and even furniture. You'd measure their temperatures, calculate how large they are, how far away they are, and how much of each one is seen by your body. Then plug all of that into the formula. In reality, almost no one goes to that level of detail on a typical project. It requires too many measurements, too much geometric data, and far more time than most design workflows allow. Which brings us to how MRT is actually estimated in building design. How MRT is estimated in practice. In real projects, engineers use a few common shortcuts and tools to approximate MRT, two of which are 1. Using globe thermometers. One of the most common field methods is the black glow thermometer, a small ball with a temperature sensor inside. It absorbs radiant heat from all directions and gives a single value that approximates MRT. It's not perfect, but it's simple, relatively cheap, and reliable enough for surveys, code checks, and post-occupancy studies. 2. Using simulation software. Tools like ClimateStudio, EnergyPlus, Ladybug tools, WUFI, and others calculate MRT automatically. They use detailed heat transfer models to estimate surface temperatures and combine them into an MRT value and even operative temperature for each zone. Most designers rely on these outputs instead of calculating MRT manually. In modern buildings, especially with large glazed facades, MRT is often dominated by window temperatures. Cold windows can pull radiant heat from your body, making you feel chilled. Hot, sun-exposed glass or surfaces can push radiant heat toward you, making you feel overheated. This is why shading systems, low E coatings, double and triple glazing, and thermal breaks are all essential comfort strategies, not just energy strategies. They shape MRT as much as they shape energy performance. Mean radiant temperature might sound abstract, but it describes something you feel every day. The warmth or coolness radiating from the surfaces around you. It explains why some buildings feel comfortable even at lower air temperatures and why others feel uncomfortable even when the thermostat says everything is fine. Good MRT is often the difference between technically comfortable and actually comfortable. By understanding MRT, designers can create spaces that feel naturally stable, balanced, and pleasant. Not because the air temperature is always perfect, but because the room as a whole is thermally harmonious. Now that we understand how mean radiant temperature shapes the way a space feels, there's another step to complete the picture. In our next video, we'll bring MRT together with air temperature to explore operative temperature, the combined metric that truly defines thermal comfort. So subscribe to the channel so you don't miss that video. Stay informed, stay inspired. TimberTalk.